Hi everybody, I'm Andrus Nispelus and I'll be talking about LDA topic models. I first ran into topic modeling when I was working at Issue, a Danish startup which is currently the fastest growing online publishing platform. My main task as the first data scientist at the company was to build an LDA topic model. Of course, I will not be sharing any intimate details on Issue's implementation specifically. Instead, I'll be talking about the idea behind the LDA itself, why does it work, what are the free tools and frameworks that can be used here, what LDA parameters are tunable, what do they mean in terms of your specific use case, and what to look for when you evaluate it. Issue as a company made its name by creating a beautiful online reading experience. You upload your PDF and it gets transformed into a sleek, clean digital publication. It's pretty awesome. But that's not where the loyal and monetizable reader base is being built. Issue has tons and tons of content, and to keep readers engaged, one must provide ways for them to navigate in all this huge pile of magazines, catalogs, books, and newspapers. That's why under each publication you see an endless stream of stuff that you could be interested in reading next. In here, the main question is what to show, where, and when. Obviously, the suggestions have to be related to what you're reading in some way, and one of those ways is to simply show similar stuff. Now, similar can mean similar reading patterns. It can also mean similar in terms of content. This presentation is about the second of the two options. So the main use case here is to find whether any two magazines would be considered similar by a human reader. All of the choices in the following slides are really influenced by this use case, so keep that in mind as you go along. But before we can even talk about publications being similar, one needs to be able to understand what the publication is all about. And for us humans, the task is quite simple. We can take a quick glance at the cover alone and we already have a pretty good idea that this is a magazine about food and cooking. It's not just a list of ones and zeros. Also, this is a magazine, so we can open it and read it. Words carry information and we're very good at understanding it. Because we have a brain, we can begin to answer questions like, what is it about? What is it related to? What does it feel like? What does it mean? We can do this quite effortlessly since we have a lot of knowledge about the world. We understand what a car is, what it's like to have a birthday, how does it feel to be happy. On top of that, we're also good at adjusting to changing context on the fly. We know how to choose the right level of abstraction, not too close, not too far, so that everything makes sense. We can easily understand that the same word carries a completely different meaning based on which context it appears in. It applies to such seemingly objective concepts as colors. Red hair, red wine, red skin, red book, same word, completely different color. Overall, we have this amazing ability to learn and understand different topics based on the words appearing in various contexts, kind of like how little kids learn a language. Now, how to put all of this, or to be more realistic, at least some of it, into a machine so that we can automate finding similar magazines and also do it in such a way that recommendations would feel almost human-like. To begin with, we're going to need three things. First, we need to feed knowledge to a machine, make it read tons of stuff. Second, we'll have to be careful with the words we use, since they're the features that carry information. And finally, we'll need to make sure the knowledge is cut into the right size chunks, since that will determine the context within which words will connect. As for the knowledge, we can safely use Wikipedia. It's broad enough, easy to download, and fun to experiment with. Wikipedia has articles about almost anything, well, at least anything that matters. And while its definition of, let's say, a birthday might differ from what each of us is thinking about, it's still a good place to start. We're not building a brain here, but we are gonna build the next best thing, a model. And just like in any machine learning process, there are four parts to be covered. First, how do we pre-process the data? In our case, Wikipedia. Then, how do we train the actual model? This is where the LDA will come into play. After that, we need to be able to apply the model on some new data. In our case, we'll be using the model built on Wikipedia to analyze any magazine. And finally, we probably want to know if we succeeded or not. To say it up front, for the first three parts, I have heavily relied on Gensim, an open source topic modeling framework made in Python. The credit here goes to this guy, Radim. Gensum is by far my favorite topic modeling tool, and I couldn't say enough good things about it. Just go ahead and Google Gensum, I'm sure you'll find it. Alright, let's start. First, I downloaded the entire English Wikipedia. It's actually just around 12 gigs. If you go to Gensum site, you'll find all the links and instructions there. Knowledge in Wikipedia is presented in the form of articles, and that's great, because it means it's already highly contextualized. Each article normally covers a single topic. It's not like it starts writing about basketball and then switches to World War II. It's actually a very important characteristic of choosing the right corpus, since the model will assume that every chunk of text we feed into it contains words that are somehow related, like talking about the same topic. So Wikipedia's internal structure gives us a good start, but it's not perfect. Wikipedia also contains tons of very small entries. We'd probably want to get rid of them, not to reinforce any unwanted word-to-word connections later. I chose to get rid of all the articles shorter than 200 words, just to be on the safe side. Next thing worth paying attention to is that Wikipedia also has a lot of entries that are not really articles as such, but metadata. They can be identified by looking at the title and, more specifically, what it starts with. I have removed all the entries that start with these namespaces. Gone. So now the corpus got smaller, but don't worry, it's still big enough. Quality over quantity. Next thing is to gather all the words from the remaining articles and sort them by popularity. Those will be our only observable features for the model, so there's no crime in being picky here as well. We can start by removing the words that appear in more than 10% of the articles, as well as those that occur in less than 20 articles. Then we can also filter words by length. We can apply different stop lists, which will vary depending on the nature of the application. We can even take this further by experimenting with features like lemmatization, different parts of speech. Just imagine building a model that would only react to nouns or verbs. Finally, we have to set how many of the remaining words should stay in the model. A good number to begin with is somewhere between 50 and 100,000. Okay, so now we got our final set of articles. It will define the window of context, and our final set of words. We can use these two to form a TF-IDF term frequency inverse document frequency matrix, which together with a list of words will be the two inputs into the model. All this so far was the pre-processing step. And I can't stress enough how important this is. I mean, the quality of the output will be determined by the quality of the input. As clear as that. Garbage in, garbage out. So provided we made the right choices so far, a model is now needed to unite everything together. Context, words, topics. In this presentation, such model is LDA, which stands for Latent Dirichlet Allocation. It was developed by David Bly and his friends in 2003, and since then has seen many areas of application: document classification, sentiment analysis, even bioinformatics. The only observable features that the model actually sees are the words appearing in documents, and there's lots of documents. Other parameters are hidden or latent, inferred. One of those is a topic that is assigned to each word, thus making every document a mixture of such topics. Notice how the model elegantly combines the three things we actually needed: topic, context, and word. Let me try to explain it in my own words. Imagine that in the world we only have three topics: politics, fashion, and sports. Each topic is expressed as a list of words with probabilities for them to belong to that topic. Let's also assume that any document can be described by a recipe of which topic and how much of it should contain. For example, 50% politics, 30% fashion, 20% sports. The model then generates such a document by taking the right number of words from specified topics and mixing them together. LDA is a bag of words model, so there's no syntax rules here. Now, you may say that's not exactly how our greatest works of fiction were created. True, but there is some truth in the model, in the way the model thinks. And if we take any article and remove the syntax, we would definitely lose quite a bit of information. It would most likely become unreadable for a human. But I bet we could still say whether it's about sports or fashion. So in some way, every document is a collection of words taken from different buckets or topics, depending on what it writes about. All this is just an imaginary scenario to show what is it that the model assumes to be the case. Now in reality, it works the other way around, though the principle is pretty much the same. Model takes an actual document written by an actual person using all kinds of words, syntax, and whatnot. In fact, it takes a lot of such documents. It assumes that the words in the same document are related, and then tries to learn a model that would explain how such document collection could have been generated in the first place if we followed the first scenario. We only need to tell it how many topics it should make and some extra rules on how they should be constructed. Okay, so maybe things are not really that simple, but in a very simplified way, that's how LDA works. Some of those extra rules that I mentioned the model requires are called hyperparameters, alpha and beta. They're both parameters of Dirichlet distribution. Alpha controlling per document topic distribution and beta responsible for per topic word distribution. A high alpha value means that every document is likely to contain a mixture of most of the topics and not just any single topic specifically, while a low alpha value means that a document is more likely to be represented by just a few of the topics. Similarly, the high beta value means that each topic is likely to contain a mixture of most of the words, not just any word specifically, while a low value means that a topic may contain a mixture of just a few of the words. To put it bluntly, high alpha will make documents appear more similar to each other, and high beta will make topics appear more similar to each other. Given my use case, this was actually a desired effect, so I kept both parameters rather high. Just in case I missed something, here's a formula. Now, as a final result, LDA model produces this file. It basically contains all the topics made of all the words with their probabilities to belong to that topic. That's it. Now, talking about the topics, how many should one go for? Let's say 5, 3,000, 476? It really depends on the application domain. Remember, my initial goal was not to label or classify magazines, but to be able to compare them, focusing on their latent similarities, and do this in such a way that it would make sense for a human reader. So once again, I ended up looking for answers on the human brain side. I already mentioned our ability to sense and apply the right level of abstraction as we perceive the world around us, but there are way more things in there. To be honest, I'm not sure if it brought me any closer to finding the actual number of topics to use for the model. I ended up experimenting with various values starting with 50 and going as high as 500. But to tell you the truth, it was definitely interesting to look into these things and try to understand what is it that we pay attention when we pick up a magazine, or what makes two of them appear similar to us. It's a far more complicated process than any LDA model. But the model is all that our little robot guy here has. And in some simplified way, it now has an understanding of topics, words, and context. And most importantly, combining it all together. Well, we now do have a model. So let's put it to the test and see what happens if we give it the same magazine from earlier. The LDA model takes this magazine, reads in the text as a bag of words. By the way, it only understands the words that were used to train the model. Everything else may as well not be there. This one is a 20,000 word magazine. I'm sure we'll be fine if we lose a few along the way. Also, I can assure you that if my model understands as little as 10% of the words in this particular magazine, it's more than okay. Unless, of course, we've trained the model on the words that carry very little meaning or are completely from a different domain. That's why the text corpus and pre-processing of it are probably the most critical steps. So, back to the magazine. After having read it, the model now tries to produce such topic distribution that would explain best how this magazine could have been generated. The distribution will have as many topics as we ask the model to make. and the height of the bars represent the fraction of words in this document that originated from a given topic. It's a probability distribution, so all values sum up to 1. Now, instead of focusing on what are the most dominant topics, we can take this thing as a whole, a unique pattern, which makes each magazine appear different enough to be separable, yet similar enough to be grouped. We could even say that a magazine, just like us, has a DNA. Now, let's take a closer look at the actual topics here. By the way, this is what I got out of Wikipedia using 300 topics. So, as you can see, they are really just a sorted list of words with their probabilities. Notice that the topics don't really have any names or labels. They're simply numbered, and those numbers don't mean anything other than a unique ID. But we are human and we like to label things, so it's tempting to do it here as well. For example, topic 81, cooking, topic 143, wine. Such labels should be taken with a lot of caution. And in my use case, we don't even need them, since the goal was not to label magazines, but to give them a meaningful fingerprint so that we can compare them. One way to compare things is to put them on a space. LDA space is a simplex, since we are talking about probability distributions here. Dimensionality of this space depends on the number of topics we asked our model to make. The stronger a certain topic is represented in a document, the closer that document is to that topic's corner. LDA spaces often have hundreds of dimensions, which is not the easiest thing to visualize. Here, for simplicity reasons, this space has only 3 topics. Now, a single magazine in a space means absolutely nothing. But once we put the rest of the 25 million documents in here, it becomes much more interesting. If we have a space, we can measure distance, and if we can measure distance, we can imagine a certain threshold within which documents inside of it will be considered similar to each other. By the way, distances can be measured using Jensen-Shannon distance, a standard way to measure similarity between 2 probability distributions, giving the values from 0 to 1, 0 being close, 1 being far away. So what do we have so far? The LDA model gave us a topic distribution for this magazine. Well, that's nice. Also, we got some other magazines that were close enough in the space. And they're even sorted according to distance. Now, before we go in and evaluate the results, let's clarify what exactly are we looking for. The only judge here will be the reader himself, reminding us that all models are wrong, but some are useful. First, we must evaluate if the model managed to capture the right aspects of a magazine in the first place. An important note here is that we are looking at the entire magazine, not an individual article in it. Secondly, we want to find out what is the right distance threshold that we perceive to separate similar from different. I can tell you it's a thin line. Magazines are a very visual medium. And that's a very helpful feature here, because we can tell a lot just by looking at its cover. Not to mention the fact that those covers were designed with the sole purpose of informing and attracting the reader in the first place. With all that in mind, evaluation here can be done by making a visual report that helps to quickly get a sense of how good the model is. A report like this doesn't do anything. It simply shows certain parameters of our previous steps, the ones that we just talked about earlier: pre-processing, modeling, scoring, along with all the distances that we get from LDA space. It's quite simple really, and can be very useful, especially if your data medium is just as visual as this. Here we can get confirmed that the magazine's neighbors are indeed similar, which is good, and since they're ordered by distance, we can see exactly where they start to differ. This will give us the similarity threshold, provided that we show enough of the neighbors to get to that point. Now, after checking a handful of such reports, spanning over a wide range of publications from different domains, different lengths, different document types, different writing styles, I can rather quickly get a feel if my model is making any sense or not, and what can I do to improve it. To sum it all up, here are my final notes or recommendations to anyone playing around with LDA models. The main point is that most of the settings will depend on your use case and the type of content you're dealing with. You absolutely have to know what are you building this for and what is the desired result. Choosing Wikipedia as the brain and Gensem as the muscle is a solid choice to start with. Pay attention to the parameters that I covered here, and most importantly, try to understand what do they mean to your use case specifically, and you should be on the right track. Thank you so much for listening. I had a lot of fun making this video. If you have any comments or questions, please write below, drop me an email, or find me on LinkedIn. Thanks.